Hey everybody, Mr. Piercy here, and we're going to be continuing our look at how to prove triangles congruent using a shortcut method, meaning we don't have to show every single little thing from figure to figure congruent. So the specific things that we're going to be looking at here is a shortcut approach called the side angle side approach. Now, we write that out as side angle side, where the way it's written, the angle literally must be in between the two sides. So looking at the diagram that we see here, basically what it's saying is that if I have two sides and an angle included in between them from figure to figure that are the same, then we have enough information to say that the triangles are congruent to each other. But the angle you can see here, angle R, I'll get my pen, angle R is in between segment RS and segment RT. Same thing with angle U. It's in between segment UV and segment UW. So those are the things that we have to recognize when we're talking about the side angle side congruence postulate. The angle literally has to be in between the two sides that you're looking at. Now, lastly, there is something called HL. And that stands for the hypotenuse leg theorem. And we'll look at that one in a little bit. That one is specifically used for right triangles only. So if you're not sure what are the parts, what they're called on a right triangle, the two sides of the triangle that make up the right angle, those are called the legs, and the side that is across or opposite of the right angle, that's called the hypotenuse. So let's take a look at how we're going to be looking at these things. Similar to what we did with the side postulate, we want to be able to write a two-column proof that shows, well, why are these triangles congruent to each other? So we have this figure where we have obviously two triangles that we can see, and Jn is given to us to be congruent to Ln, Kn is congruent to Mn. And we want to prove that the triangles are congruent to each other. Now, I want to preface this by saying that the diagram is skewed. The idea that they're going for here is at some point we want to look at this angle here at 1 and this angle here at 2. And the reason why they're going to say that those are congruent to each other is because they're vertical angles. Well, those don't really look like vertical angles, but that is the idea that they're trying to go for. I think maybe that just missed something in editing because the figure wasn't quite properly made for vertical angles. But that's the idea that we're looking at. We're seeing that NJ and NL are congruent to each other. That's given. NK and MK and NM are congruent to each other also because it's given. So if we see the angles in between the sides, well, that's enough to be able to say the triangles are congruent because of the side angle side conjecture. Here in the diagram, we have a rectangle. What can I conclude about triangle ABC and CDA? So essentially we have a rectangle that we're constructing a diagonal in between them, and we want to know, well, what can we conclude about the two triangles? Well, before we start actually thinking about how to prove it, well, let's just don't look at the solution stuff. The solution is there for you as kind of a framework to help you figure things out. But when you actually have to do this on an assignment, when you actually have to do this for a quiz, that stuff isn't there. So let's just pretend it's not for the time being and say, okay, well, what do I know about a rectangle? Well, the opposite sides in a rectangle are the same. So because I have, and it looks like the part vertex D is missing, because I have side AD and side CB, those would be congruent to each other. Same thing with AB and CD, those would be congruent to each other. Well, an angle D and angle B that's in between them, those would be congruent. So we could say that those triangles are congruent by side angle side. So that's kind of what we're looking at here. Now, side obviously could have been used because the diagonal AC is the same in both triangles. So there we go for that one. Again, just look at the diagram to see what do we know has to be congruent, or what do we know about the figure. Mark some things on it and start thinking about how we can show the triangles are the same. So what I'd like you to do here is just go ahead and take a moment, pause the video, and try, can you prove why these are the same? Now I'm going to let you know that when I did them, I wrote them out as a two-column proof. Now I'm not saying you have to. To me, it just seems to make more sense to do these this way. So that's how I presented my answer. So go ahead and try proving these two statements, and when you're done, hit play and come back and check to see how you did against compared to my answers. All right, so let's see what we know about the figure. Well, it tells us in the information AD or A, B, C, D, and E, F pass through the center of M. It's a circle. So because circle M is using AM, DM, and so on, we know these sides have to be the same because they're basically the radius of a circle. And it's giving us that angle 1 is congruent, that all four of these angles, 1 is congruent to 2, is congruent to 3, is congruent to 4, that all of those angles are the same. So how can we prove that triangle DMY is congruent to triangle BMY? Well, based on the information that we have, we can say that BM and DM are the same because that was given to us. Same thing with angle 3 and 4. Well, the one thing that we have to include is that MY is the same between both figures because, well, it's shared between them. That's the reflexive property. So we have a side, an angle, and another side where the angle is included in between the two. So that's enough to be able to say that the triangles are congruent by side, angle, side. So let's clear this up here and let's start taking a look at the next one. Okay. Here, what can I conclude about AC and BD? Well, again, we know these things are the same. This angle, this angle, this angle, this angle. What do I know about AC and BD? Well, looking here, what I was able to say is that MA and MD are the same because they're the radius of the same circle. AMC and DMB, those are vertical angles, so they're the same. MC and MB also are congruent to each other because they're the radius of the same circle. So the triangles AMC and DMB have to be the same. So that means that AC and DB would have to be the same because corresponding parts of congruent triangles are also congruent to each other. So that is how I'm going to write the proofs for those two particular problems. Again, if you have any questions about how I'm coming up with these or struggling with writing a proof yourself, let me know and we can practice it. Come to see me in office hours, or at the very least, shoot me an email, leave me a comment in the classroom. So here we have a hypotenuse leg congruence theorem. Basically, this is something that can be used only with a right triangle. Generally speaking, and there's another video that I made that goes along with this that demonstrates why. Generally speaking, what we see here is I have a side, and an angle. Same thing here. I have a side, and an angle. And usually what we would say is that that combination of parts, side, angle, does not work to prove triangles are congruent. Side, angle is actually going to produce two possible triangles as opposed to one unique triangle. And that's why we say we can't use that combination of parts to prove triangles are congruent. That's actually going to be something that'll appear again when you take pre-calculus. When you're doing trigonometry in pre-cal, you'll see something called the law of sines. And there's a special case when you're talking about the law of sines that uses the combination of a side, and a non-included angle. And it revisits the idea that there's two unique triangles that are created, not just one. Well, the reason why this one works is because it's a right triangle. This works essentially because the Pythagorean theorem says it must. If I know two sides of a right triangle, the Pythagorean theorem guarantees me what the third side's going to be. So there's nothing that I can use with a right triangle if I know two sides, I will always be able to figure out what the third side is because that's what the Pythagorean theorem is. Or the Pythagorean theorem guarantees that anyway. So the hypotenuse leg theorem isn't so much a hypotenuse leg or just a side-side angle combination. It's really, because of the Pythagorean theorem, it's just an extension of the side-side-side congruence postulate. And leg is also a good way of proving right triangles are the same, and it works for the same reason. This one looks a lot more like side angle side, like what we see here, side angle side, side angle side. But the Pythagorean theorem would also say if I know two corresponding sides of a right triangle are the same, the Pythagorean theorem guarantees that the third side has to be the same also. So there are two unique ones for right triangles, hypotenuse leg and leg. So let's take a look at this triangle here. Write a proof to show that triangle ABC and triangle EDC are the same. Well, I'm going to take the information that they gave me and I'm going to start marking up the figure. I'm going to just pretend that the proof isn't even there for now. So AC and EC are the same, and they're marked for me already. Well, AB and BD are perpendicular to each other, so I'm going to mark those as a right angle. Same thing with ED and BD. Well, it also says that AC is a bisector of BD. Well, if AC bisects BD, then BC and DC have to be the same. So looking at the way that we've marked it, BC and DC are a leg of a right triangle, and AC and EC are the hypotenuse of a right triangle. So in my proof, I'm probably going to want to try and use that hypotenuse leg theorem that we just talked about. So I'm going to take the information that was given to me, and I'm going to use that first. Well, because we have perpendicular lines, we must have right angles that are congruent to each other because all right angles are congruent. And if I have a right angle and a triangle, well, that's the definition. That's how we classify a right triangle. So AC is a bisector of BD. Well, that was given to me. And BC must be congruent to DC because, again, that's the definition of what a bisector does. So that means we can say that the triangles are congruent to each other by the hypotenuse leg theorem. So there's an example of how we're going to use that one. Now this one here, not exactly my favorite example in the world, but it's basically letting you understand is that, well, here is an extension, here's an application for it beyond just the textbook. Why would we, necessarily want to have an idea why these things are the way they are? So here we have a gate for a ranch that's in the form of a rectangle, and well, what do you know about the triangles AFC and EFC? Well, what would you use to show that triangle ABC and EDC are the same? Well, so here, this is essentially a paragraph proof. All this stuff is stuff that you would produce yourself. Okay, but for the purposes of our notes, we can just kind of fill in the blanks. So you're given that the quadrilateral is a rectangle, so that means angle B and angle D are right angles. Well, the opposite sides of a rectangle are definitely congruent to each other, so that means AB and ED have to be the same. So you're also given that triangle AFC and EFC are the same, so that means AC and EC are the same also. So the hypotenuse and a leg of each triangle is congruent, so that means we can conclude, we can use the hypotenuse leg theorem to conclude that triangle ABC and EDC have to be congruent to each other. So here we go. This is coming up to the end of our lesson here. I want you guys to go ahead and, again, try and answer these questions independently. Or if you're sitting with partners, you can discuss it, obviously. But I want you to try and come up with a solution to these two questions here. And then when you're ready, come back and compare your answers with mine. All right, so let's take a look at the number 3 here. Explain why a diagonal of a rectangle forms a pair of congruent triangles. Well, here, the diagonal of a rectangle is essentially the hypotenuse of a right triangle. And since the hypotenuse is congruent to itself because it's shared between the two triangles, we could really say that the triangles are congruent by side, side, side. But because the right angle is in between the two legs of the right triangle, we could also use side angle side as the right angle where it's the included angle. And last but not least, in example 4, what would happen if the quadrilateral that we had were squares instead of rectangles? Well, essentially a square is a rectangle. So the same reason that I used to explain my stuff in answer 3 is the same reason why I can prove those triangles are congruent to each other. And obviously this should be triangle ABC, not angle ABC. So that's pretty much it for the lesson that we have on proving triangles congruent by side angle side or the hypotenuse leg. Just keep in mind that the angle must be included in between the two sides. If it's not, we're not going to be able to use side-side angle to show triangles are congruent to each other. So if you have any questions about things that we've gone over, anything especially about the proofs, because we are going to be doing more and more proofs, be sure to let me know. Send me an email or leave some comments for me in the post to the classroom. I'll be happy to work with you on whatever questions you have. But until then, until next time, guys, thanks for watching and be good.